Yes, sir, we'll start.
Again, a very good morning, everyone. And today we have a small agenda where we'll be covering, 2, 3 things. Uh, Today, primarily, we'll be focusing on how to deal with imbalanced data sets. What are the different techniques available? And we'll be implementing one such technique called as SMOTE. And there is a whole lot, an independent library where you can find other techniques as well to deal with the imbalanced data set. And we'll be taking up one case of stroke prediction. We'll be dealing with highly imbalanced data set. And if time permits, I'll be you discussing a little bit that how you can create a simple web application using Flask, and how to deploy your machine learning model that can run at the back end of one web application. And yeah, so what is the imbalance in the data set and what problems can it cause? Any quick thoughts on that? Any quick comment? What is imbalance? Why it is needed to deal to mitigate imbalance in the data sets? Yes, anyone? Are there real humans behind these names? Akanksha, Amarnath, Anthony, Bindu, Dr. David, Mahesh Lokhande, Guna Sundari, Rubai.
We have a response from the chat.
Okay.
We have a response in the chat, sir. Uneven sets for each category by
Uh,
Mishra
okay,
madam.
but I cannot see any response in the chat. Yeah, so there is Harshvardhan. Okay, sir. Shruti Mishra. That's what is imbalanced data. Okay. I think I missed some of the messages. They went somewhere else.
Okay, our first message was uneven sets for each category.
Yeah, yeah. And even set for each category, that is the response from Shruti Mishra. Thank you, Shruti, for responding. Okay, so I would like to hear one or two voices so that I can get an impression that for next, 2 hours, I'll be speaking and some real Homo sapiens human beings will be listening to that rather than just talking to my monitor and looking at my face and possibly Professor Chandramouli.
I am listening to you, sir. You feel like I am there here.
Yeah, so where is Professor Lakshmi? So she was there in last session and was the source of motivation for me to talk.
Yes, exactly.
Okay, so that's great. And let's take it forward. So for today's, some of the essential material that I've shared in my drive, and I'm putting up the link here. So there are 3 files, two notebooks, and one dataset file. You just quickly download them from this particular location and upload them somewhere in your drive. Class imbalance or imbalance in the data set is a very naturally occurring problem, because if you're dealing with disease classification, or you are dealing with certain type of other scenarios including forensics, then there is a use class imbalance that exists in the data set. Suppose you are trying to detect whether a person uh, is going to have a certain type of cancer. So you are screening suppose 1,000 patients, so maybe 3 patients are detected with cancer, and you label them that this is the cancerous data and these rest of the other samples are non-cancerous. So in healthcare domain, this imbalance is automatically kind of reported, and this is how the data sets are formed. So suppose there is an imbalance in the data set that 95% of the class of the samples belonging to a particular class, and there are just 5% of the samples that are belonging to another class. So there is an imbalance of 5 is to 95. So 1 is to 19 sort of imbalance is there. If you train a classifier and classifier does not learn anything and it just labels that whatever data it sees in the real life, it labels that with the majority class, then still its accuracy will be 95%. But here you can see that it is of no use, because it is just dumbly labeling the class, the unseen data with the majority class. And this is how this is why we need to mitigate this problem. We sometimes just accuracy may not be kind of necessary metric. There are other metrics which can take into account the false positive, false negative rates, sensitivity and specificity, for that matter. And we need to evaluate the accuracy from that perspective by taking into account uh, AUC, ROC, AUC scores, and other things. And we need to try to create a kind of balance in the data set. And there are different techniques for for class balancing that researchers have suggested, and some of them are very extensively used. So today we are going to have a brief overview of a special library which is called IMB Learn, or that is Imbalanced Learn library. And that provides some of the techniques and their implementation in the form of Python API that you can use. So we'll be talking about a little bit about this IMB Learn library, and we'll be using it. So let me share my screen. Hope my screen is visible.
Yes, sir.
Okay. So you can just Google this IMB Learn library. It is imbalanced Learn library, and it comes with some documentation that how to get started, start with this, what it can do. And yeah, so installation is very easy. It is just like let's move to the user guide. So there are different algorithms that we can use for class imbalancing. We can create a kind of balance in the class. So when we let's take a very simple example of binary classification, like you are predicting or you are detecting a disease, and there is a imbalance in the the class samples. Suppose you are going to predict whether a person is going to have heart stroke, going to have a brain stroke in next 5 years, or going to have a diabetes in next 5 years. So what is the likelihood? So there are just two class levels, 0 and 1, and there is an imbalance in the data set. So and the imbalance is suppose 5 samples for disease class, and 95 samples for the normal class. So there is an imbalance. So how you can mitigate this imbalance? There is majority class and there is minority class. So there are two basic steps that you can take. you can downsample the majority class. Suppose there are 95% samples of the majority class, so you can reduce it to half or quarter in number, or you can increase the samples of the minority class. So you can downsample majority or you can upsample minority class. So downsampling the majority class is very easy. So suppose there are 1,000 samples belonging to majority class. So what you can do, you want to just uh, do downsampling with a ratio of, suppose you want to halve these samples, then you can just delete 50% of the samples, and that is the simplest way to downsample. But upsampling is a major task, and most of the class balancing techniques are focused that how to upsample the data in the minority class, and there are different techniques for that. And there is one technique which is synthetic minority oversampling, or that is called smooth. So that is very extensively used, and there are uh, different types of variants behind minority oversampling techniques. So how to generate the new samples or synthetic data? So either you can use just a simple k-neighbors classifier approach, where you are looking at the minority points in the feature space, and you are generating some of the data in the neighborhood of a minority sample. Or you can use support vector machine way, that how you can generate new data, and there are different implementations for that. So here you can see that what this imb learn is. So this is just a library that contains implementation api for some of the techniques that can be used for imbalanced learning, and that's why its name is imbalanced learn. So we have sklearn, and similarly we have this imbalanced learn library, and its sole purpose is to provide necessary tools, necessary api functions that can be used to make the balance in the classes. uh, yeah. So it is very detailed. There are many examples given to this, and if you want to explore it in more details, so we'll be covering some of the techniques. We'll be focusing on smooth today, which is synthetic minority oversampling technique. But if you want to explore some of the other techniques or other variants of smooth, then you can refer the documentation of this particular library, and that is IMBLearn. So the link that I have shared with you to download the data, so it contains basically these three files. So this is stroke shared. So the copy of data. So this is the stroke data that we'll be using today. Copy of dealing with imbalanced data set. So this is some of the basics that how to use IMB library, and this is uh, the file where the code related to this particular data is there. So we'll be discussing these things, and we'll be talking about the stroke prediction, that what it is. We'll be comparing some of the techniques, that which technique performs good. We'll be exporting the best possible model, and we'll be creating a small application, web-based application using Flask, and we'll be running our model behind that. And so that's the pretty much agenda for today. And let me yeah come back to this. So how to use IMB learn library and what does it mean? So let's take some of the examples by creating some of the synthetic data, and let's see that how to deal with imbalanced data set that will be creating synthetically. We'll be generating make classification method, and if this library is not installed on your system, so you can install it with this just simple pip command, and that is sudo pip install imbalanced learn. So most probably when you are running it first time, it will not be installed on your system, but if it is already there, then it will show you this message that it is already available with your system, so you can try it. And generate and plot a synthetic imbalanced classification data. So here in our first step, what we'll be doing, we'll see that how to create some synthetic data set with the imbalance in it. So sometimes suppose you have developed some strategy to create a kind of balance in to classify imbalanced data, and you do not have an access to the data set itself. So what you can do, you can work with some of the synthetic data sets that you can generate very easily. So here we are importing some of the packages, like we have imported this counter class from this collections package. So this counter will be very handy to calculate the number of samples belonging to each of the classes. And from sklearn data sets, so this is sklearn is scikit-learn library that is pretty much used for machine learning. And it contains many traditional machine learning algorithms and different modules around them. And there is a some module that is called datasets, and you can import make underscore classification method that can be used for creating uh, or for generating synthetic datasets. And for doing some sort of plotting, we'll be importing this pyplot from matplotlib, and we'll be using this particular function where to check some conditions. And let's create a synthetic data set. So for creating synthetic data set, we call this function called as make classification. So it is used to create a you know uh, to create a data set for classification. And what will it have? It will have number of samples. So there will be 10,000 records or 10,000 samples in the data set. And there will be two features. So the X will have X1 and X2. So this is the number of features, and there will be one class level. And there will be no redundant or repetitive feature. A number of clusters per class means there will be no any subclusters in the class, for the classes. So by default it is two, but if you do not want to have any more clusters or any subgroups, then you can keep it one. And this is weights. So we'll be having two types of classes, and we'll be assigning these weights 0.99. So the majority class will be having 99% of the samples, and uh, the rest of the 1% samples will be belonging to the minority class. And the flip y, so there will be no kind of overlap between these two classes, or there will be no random generation of the samples. So there will be clear distinction between these two classes. And to make this data set reproducible, we are making random state as one. And this is used for kind of reproducibility, to add some sort of reproducibility in your data set. So every time you run this particular code, you will get the same data set uh, with the help of this random state as one. And this particular function generates one synthetic data set. So we'll be repeatedly generating some of the synthetic data sets, and we'll be seeing that how effective our techniques for undersampling and oversampling are, and we'll be seeing them with the help of simple visualizations. So this particular function make classification is being used for creating one synthetic data set with the class imbalance of 1 is to 99. So 1% of the data will be belonging to minority class, and 99% of the data or the samples will be belonging to the majority class. And then you can easily count the number of samples in each of these classes, and that's why this uh, you know counter class coming from this collections package. And you just need to pass the value y, so that is just the class level, and it will give you that how many samples for each of the classes are there. and then you can print this counter, and then you can call this, simple. You can pick up each of the functions and each of the points, and you can just create a scatter, plot around them. And for each of these, there are, because there are two values in the x, so there is value 0 and 1 because number of features is 2, and there is one class label associated with that. So we'll be depicting these, this data set. So category 1 is being represented with this kind of orange dots, and category 0 is being represented with the help of these blue dots. And here we are printing the number of samples. So you can see that 9900 samples are belonging to category 0, and only 100 samples are from category 1, and there is an imbalance of 1 is to 99 in this data set. And this is how it is being depicted like this. So this is the scatter plot for our two classes, and there is an apparent or very clearly visible, imbalance. There is majority class, and there are just 1% samples of the minority class. So so this is how to generate an imbalanced synthetic data set. Now oversample and plot imbalanced data set with this mode. So we'll be talking about one oversampling technique that is called uh, uh, synthetic minority oversampling. So this is a very popular technique, and it was proposed some researcher, some Indian researcher, maybe Nitesh Vadhva or Arora. So he proposed this technique many years before, and there are some improvements around that technique, or variants around that technique as well. So let's see that how to use this smooth technique, and that is synthetic minority oversampling. So in its implementation, they used k-neighbors. Sorry, yeah, k nearest neighbors sort of classifier that they if there is some minority point, then what are the other neighboring points around that. So connecting the lines between the neighboring points, two neighboring points, so they generated other synthetic points around those lines. So that is the very basic sort of description of the implementation of this algorithm. And how does it work? Let's see that what are the different functions and classes that you need to import from the Imbalance library. So we'll be creating the synthetic data set again, and we'll be applying smooth on that. So when you apply smooth, so by default its behavior is that it will create an equal balance between the classes. So suppose there are 9900 samples of the majority class, and there are just 100 samples of the minority class. So in its default behavior, it will equally balance both the classes. It will generate as many samples for the minority class, which can make the number of classes and majority class equal to the number of samples in the minority class. So that is the default behavior, but you can change it, and we'll be seeing it that instead of creating kind of equality, because that is not a very good idea, because once you generate too many examples or too many samples synthetically, then the, the noise may incur in the data set, or it may not be that effective. So let's see. So some of the code is redundant. We are importing this counter class from the collections package, and from sklearn dataset we are importing this make classification, and from Imbalance library. So Imbalance library is a very rich library, and there are many sub packages in that library. So there is a sub package called as oversampling. So for oversampling, there are different techniques like adsin, smooth, smoothen, and others. And from oversampling, we are importing this particular class that is smooth. So we'll be instantiating this particular class. We'll be creating an object around that, and will be kind of doing some transformation on our data set to create balance in our this synthetically generated data set. So this pie plot and where to check the condition, and we are generating this synthetic data set. We are generating 10,000 samples, and we are counting that how many number of class samples are there for majority and minority class. So that is this repetitive code, and the new line of code is to instantiate this smooth class, and we are storing it in this oversample variable, and this oversample variable can be used for doing transformation over our data set. So oversample dot fit underscore resample is the method that will do the uh, upsampling for the minority class, and we are just passing our data set, the features and the class labels for fit underscore resample. And by default, what it does, you can pass that what sampling strategy you want to follow. So that is just a hyperparameter that can be passed to this mode. But for the time being, if you are not passing any data, any extra kind of parameter to this particular uh, uh, this is mode, then it will by default create equality for majority and minority class. And once it is called, then there will be new transformed data set that will appear in X and Y, and you can again counter or count the number of samples in majority and minority classes, and you can print that uh, how the number of samples in each of these classes have changed, and you can print it uh, whether there is some sort of balance in the data set or not. So once you execute this particular cell, then you can see that uh, before kind of oversampling, the number of samples was 9900 and 100. So there was an imbalance in the data set that we initially create, and after calling this mode, you can see that the number of samples in both majority and minority classes are same. So it is 9900 for class 0, and for class 1 9900 as well. So this is how the mode can do, and what it is doing at the backend, it is running kind of uh, forming uh, neighbors, finding out the neighbors of the minority samples and generating new data set around those neighbors. So here you can see that wherever there were some points now, the new samples have been generated around them, and the space belonging to the minority class have kind of thickened, or there is a density involved around the points. So new samples have been created, and you can tweak its behavior. There are different hyperparameters available with this mode. So by default, the number of neighbors that are involved in this in generating these samples is 5. But if you want to keep them 3, 4, or 7, so you can further kind of tweak it and kind of see that which works best for your particular kind of problem. So this is how simple smooth can be applied on any synthetic data set to create new samples, and that is very easy. So you just need to import IMBlearn library, and from there is over underscore sampling sub package, and from there you can import smooth. So you need to instantiate this smooth, and by default it will create equal samples for both minority and majority class. So it is basically an upsampling technique. It will not do anything with the majority class, but it will just play around minority class and will create new samples for that. And then you need to call this particular function, which is fit underscore resample, and it will transform this data set and will create kind of balance as far as number of samples is uh, is concerned. So this is how to apply smooth, and In research, it has been established that smooth alone is not kind of sufficient, because if you just create new samples and because there is huge uh, imbalance between the class levels, so it is a good strategy to follow oversampling with undersampling. So undersampling is just to reduce the number of samples in your majority class, and oversampling is to increase the number of samples in the minority class. So that is the kind of proven strategy to make the most of this imbalance kind of step. So we'll be seeing that how to do smooth along with random undersampling. So you can do random undersampling, you can manually delete it, or there are some methods available that is called random undersampler, and that is available inside uh, undersampling subpackage inside Imbalanced. So let's see that how to apply it together, smooth and random undersampler uh, for our this synthetic data set. So we are importing the same packages, but here the new package that we are importing is undersampling. So under and underscore sampling. So this is the name of the package which is available inside IMB learn, and from there we are importing this this particular class which is random under sampler, and it would be used for undersampling the majority class. And because this smooth and random undersampler has to be performed on the same data set, so they will work, or they are kind of applied in the form of a pipeline. And there is a a special sub package inside this IMB learn library, and that is pipeline. And from there we can call this particular class, that is pipeline. So it will be creating a pipeline of smooth and random undersampler on the same data set, uh, uh, in the step by step manner. So this particular technique is very extensively used, the smooth and random undersampler, for imbalanced problems. And the rest of the packages are same. So we are doing the same steps. We are making a classifier by calling this make underscore classification function. So synthetic classifier is being created. And in our next step, we are counting that how many samples of each of these classes are there, and then we are defining this pipeline. So pipeline is just a kind of systematic application of a smooth and render undersampler on our data set, and it can be automated, and that's why we have this pipeline sub package to take care of this thing. And here, interestingly, we are defining our sampling strategy. So we are creating this sampling strategy, because creating equal balance is not a good idea, and you need to do some sort of experimentation on the data set, that how AUC and ROC values are changing, how false positive and false negatives are changing on your validation set, whether your model has been generalized, or there are certain issues with the model. So this is something that you need to take into account through experimentation. But here sampling strategy provides you that instead of having the common the default behavior of smooth, where the minority and majority classes are just capped at the same level, because as we saw that the smooth by default generated 9900 samples, and that was equal to the number of samples in the majority class. So here you can see that there is an imbalance of 1 is to 99. So that is 1 is to almost 100 the kind of fraction is there. But here the sampling strategy would be there, that instead of having 1 is to 100, let's keep it 1 is to 10. So that is something we should get started with. So we are multiplying the number of samples by value of 10, so that it becomes 1 is to 10 instead of 1:100. So here sampling strategy, it can take a value from 0 to 1, and by default it is 1, that there will be equal ratio of minority samples versus majority samples. But here we have capped the strategy as 0.1. It means that there will be a ratio of 1:10. And then you are doing random undersampler. So after this step, it will look into this, that what should be the final ratio. So we are generating new samples for this minority class, and we'll be doing some undersampling on our majority class, and the final ratio should be 1:2. So here the sampling strategy is zero point 0.5, that after generating some new samples for minority class, we should reduce some samples from the majority class, so that the final ratio becomes 1:2, and that's why our sampling strategy is zero point 0.5. And here we are specifying the stats, because this is the parameter that we need to pass in our pipeline. So O is for over and U is for under. So we'll be taking these two steps, and this is a standard way to write uh, uh, these steps: oversampling or undersampling, or how you want to perform. First you want to do undersampling and then oversampling, or you want to do oversampling and then undersampling. So you can test both these ways, which works best to increase the AUC ROC value or score, or the area under curve, uh, or the false positives or false negative rates. So this is just a pipeline, and here we'll be taking these steps, like first oversampling and then undersampling. And uh, the instance of this pipeline will be used to call this fit underscore resample. So in earlier example, we just used smooth, and here we are using a pipeline of undersampling and oversampling. And let's see that what it does and how our data set is transformed with this strategy. So here we are printing before and after this transformation, the number of samples, that how it is transformed, and then we'll be printing this uh, that how the distribution is there. So here you can see that at the starting, the imbalance was 1:2, almost 100 or 99. And after these two transformations, we can see that it is 1:2. So the imbalance ratio is zero point 0.5. So there are 990 samples belonging to minority class, and there are 980 samples belonging to majority class. So this is how this pipeline of undersampling and oversampling is kind of taking place. And yeah, so let's move ahead, that how to evaluate some classifiers and how well they are performing. So as I told you, that for imbalanced classifiers, uh, if you just train a classifier on the imbalance data, suppose there is an imbalance of 1:99, and even if you do not train any classifier, and you just write a simple if condition, that whenever there is some sample, you just need to label it that it belongs to majority class. So it will have 99% accuracy, but it is of no use, because you have not trained any classifier, or even if the classifier is trained, then it may get skewed or biased towards the majority class. And that's why we need to take it very carefully. We need to create some balancing strategies, and we need to perform various things. And apart from accuracy, precision, or recall, we need to take into account some other measures, like for if it is multi-class classification problem, then we should take into account confusion matrix or AUC ROC scores for different p values. And uh, this is how the problem should be kind of mitigated or solved. So here we'll be evaluating uh, decision tree classifiers and on imbalanced data, and we'll see that how their ROC AUC scores are changed with different strategies. So at the starting, decision tree evaluated on imbalanced data, and without doing any sort of balance on the data set. And here we'll be using k-fold validation, and that is repeated stratified k-fold validation or strategy that we'll be using. So let's see that what we are doing. So we are just creating an imbalanced data set, that is synthetic data set, and we are using the same function, make underscore classification, with the same parametric values. And then we are creating an instance of decision tree classifier. So this classifier is available inside sklearn, and there are dozens of classifiers available. So in tree subpackage, there is a decision tree classifier. Inside svc package, svm package, there is svc classifier. In linear model, there are other types of classifiers available. So here we are importing this decision tree classifier and making an instance of it. And we are using repeated uh, stratified k-fold. So it is a very kind of a very popular technique for validation. Like if there is a data set, then you can create sub data sets out of that, and you can test the accuracy of your model on different data sets, and you can see that how well it is performing. So here we are using repeated stratified means that if there are classes and there is a particular ratio in the data set, so it should not be like that, that whenever you are creating subsets from the data set, so there should be a sort of proportionate representation of samples from each of those classes, and that is what the stratification or stratified means, and we'll be creating k folds. So here we'll be repeating this step. So number of splits is 10. So we'll be dividing our data set into 10 different parts, and we'll be repeating this particular process for 3 times. So what will be kind of creating here, 10 into 3, so we'll be creating a sort of 30 decision trees being trained from these different subsets coming out from our data set. And we want to make these results reproducible, so that if you execute them more than one time, so you get the same sort of split every time. But if you want to keep it just random every time, these these splits or these uh, k-fold validation process takes place, then you can just remove this random state. But we want results to be reproducible, and that's why we are making this random state as 1. And once it is done, then you can see that what is the
ഇത് ലീവ് ചെയ്യാനും പറ്റുന്നില്ല.
is pardon.
You continue, sir. I have muted.
Okay, no issue. All right, so in nutshell, we'll be creating 30 decision tree instances, and we'll be evaluating that how well they are performing. So this is just a kind of validation process that is very much used while evaluating any classifier, and we'll be seeing the average accuracy. So here we are not just measuring the accuracy, here we are measuring the ROC score, because ROC score AUC, area under curve score, is a kind of very much used performance metric for imbalanced classification problems, because accuracy can present just an illusion, because accuracy is having 99, but it is not having that it is not taking care of the false positive and false negative rates that well. So that's why we take into account area under curve metric. So what we are doing, we are just measuring that how well these 30 decision trees performed and what AUC score they uh, kind of yielded. So here we are just calculating the mean of these scores. And here you can see that this is our imbalanced data set, and we are performing this repeated stratified k-fold sort of validation process. We are evaluating 30 different instances of decision trees, and the mean ROC AUC score is uh, 0.761. So it is just giving you an idea that it is almost 76% sort of effective. And let's see that how to improve it further. And let's see that whether these smooth or smooth and uh, random undersampling technique, do they actually perform? Can they really improve this ROC AUC measure, or what effect they put on this overall process? So let's move ahead. Now we are moving decision tree evaluated on imbalanced data set with smooth. So we are bringing in our one weapon from our arsenal, and that is smooth. And then we'll be bringing in random undersampler, and we'll be seeing whether are we able to improve this ROC AUC or not. So most of the code happens to be repetitive, and we'll be applying this smooth, and let's see that how it can improve and what it can do. So this is our model, which is decision tree classifier, and we'll be applying this pipeline with this uh, with this smooth. And we are doing the same step. We are creating your number of 10 number of splits, and we'll be repeating that 3 times. So total 30 times we'll be doing that step, and we'll be checking that how it performed on different sets of the data. So we are not taking just one instance of the data and giving you an accuracy that it performed well. So we'll be creating different combinations as the subsets from the data, and we'll be evaluating that how well it performed on different uh, uh, decision tree instances, and what is the average accuracy. So this is what we have done before. And after doing this, after bringing in smooth into action, here we can see that from this AUC score of 0.76, we have improved it 0.82. So here you can see that there is kind of uh, some improvement on AUC ROC score. And let's see whether it can be further improved if we apply a random undersampling with smooth, and whether it is really effective or not. So apart from this smooth, there are other techniques available here. Like there is a complete complete documentation, like what other techniques you can apply here. What are the different techniques for oversampling? What are the different techniques for undersampling? And which technique works best for you? So you can just, like, there is another very important and very frequently used technique, that is addition, and uh, you can use it. So that is adaptive synthetic sampling method. So you can also try it and can see that how ROC AUC scores change for your particular problem, and which is the most suitable technique that you can apply for a particular kind of problem. So here we are applying decision tree on imbalanced data set with smooth plus random undersampler. So here we are importing some of these repetitive packages, and also random undersampler package. So we'll be creating a pipeline where there will be oversampler and undersampler, and here we are passing the instance of our model, that is a decision tree model, and we'll be creating a pipeline, and we'll be applying it on the repeated stratified k-fold validation process, and we'll be measuring the mean ROC AUC scores. So here you can see that it has it has done a sort of improvement. Earlier it was 82 with just smooth, and here you can see that after applying smooth, it is smooth plus a random undersampler. It has improved it further, and here you can see that ROC AUC score is 0.84, and the rest you can try and test other techniques as well, and can pick up the best strategy for your method. And there are different parameters that you can tweak, like sampling strategy is one of them. Here the sampling strategy is 0.1, so you can see it that what happens with 0.2 and 0.3, zero point 0.4, and what happens if you change it to 0.4 and zero point 0.6. So you can plot different sort of graphs and charts, and can see that how the performance is improving or deteriorating, and which are the best possible parametric values that you can use for a particular piece of problem. So this is just a kind of overview that how to use some of the class imbalancing mitigating strategies. What is smooth, what is random undersampler, and how to create a pipeline, and how to create a balance in the data set. And this is for sklearn, but this Imbalance, there are some packages available if you want to work with the image data, if you want to work with sklearn, or if you want to work with artificial neural network, then you can do that. And almost every API, suppose if you're talking about sklearn, and we are using this keras library for image classification, so they have their some mechanisms to overcome this imbalance problem. Like in uh, keras, there is class weights, so you can specify the weights of the classes. Suppose there is an imbalance of uh, 1 is to 2, or there are just 50% samples and 100% samples, 50 and 100 samples from minority and majority class. So you can assign class weights, and at the time of training it can take care of that. But if you want to use this particular library, it can also be used in that sense, uh, if your data set is imbalanced. So now let's move towards to see it on some practical and some big data set, and that is called stroke prediction. So let's take this discussion to the stroke prediction, and this is the file stroke prediction IPynb. Okay, so this data set is there. There are 5,110 samples in this particular data set, and there are 12 columns in this data set. So there are actually 11 features and one class level. And this particular data set, uh, you know, uh, uh, contains whether a person is going to have a stroke or not based on these values. Like there is ID, so that is just the patient's ID. There is gender, that is categorical value that can contain categories male, female, and others. There is age, there is hypertension, there is some pre-existing heart disease, marital status, work type, residence type, average glucose level, uh, BMI, smoking status, and whether the person is likely to have a stroke or not. So there is a class level that is just a binary valued column. And it is a very highly imbalanced data set, and it contains some of the challenges that a typical data set contains. So there is a mix of categorical as well as numerical values, so we'll be dealing with that how to convert all the values to the numerical values. Because after all, you cannot train a classifier on the numerical on the categorical data. So everything that a classifier can accept for training should be in the numerical form. There are certain missing values that we'll be dealing with. So these are some of the kind of uh, EDA techniques or kind of data preparation and cleansing techniques that you can apply, and that almost any typical data set suffers. So there are different libraries for pre-processing data, for doing certain types of transformations on your data. And pandas is a very extensively used library for data exploratory data analysis. You can do some sort of visualizations. There are different libraries available for visualization. Matplotlib is very commonly used library. Seaborn is there. If you want to make interactive plotting, then Plotly is there. And there are different other libraries that can be combined with Python. And let's see what is there in this code. So there are certain packages. So we'll be doing exploratory data analysis, we'll be doing data wrangling, munging, cleaning. So we are using this pandas library, and we'll be using it as PD for the sake of uh, to make it handy. Instead of writing every time pandas, we'll be writing PD. We'll be using sklearn, which is scikit-learn library, and some of the sub packages from this scikit-learn library. So we'll be splitting our data set into training and test, and that's why we need to uh, import this particular function, train test split. So you would be aware of this package because it is very extensively used, and it is there in almost any machine learning pipeline. So this is the basic basic steps that first we need to split our data set in training and testing. And there is a model selection subpackage inside sklearn. And then metrics. So there are different performance metrics that you can use for testing your classifier. Like in the last example, we saw that how to use ROC, AUC, but there are other metrics as well, like accuracy score, confusion matrix, classification report. So if you want to display the precision recall, F score, and other measures, so classification report is a very kind of handy metric that you can readily see that how well your model performs. And we'll be working on different types of classifiers, and there are different sub packages for different classifiers, and you can explore it further, that what are the different classifiers available with sklearn. So from SVM sub package, there is SVC classifier, support vector classifier. And from neighbors, we have this KNN classifier. From tree, we have decision tree classifier. From knife base, we have Gaussian knife base. And for from linear discriminant, you can import LDA and different logistic regression. So there are different classifying classifiers available. And our data set is available in the drive. So what you need to do, you just need to, so data set is this one. And it contains 5110 values. And we'll be seeing that what our data set looks like, how many columns and rows are there, and what problems does it have apart from imbalance. So we'll be mitigating those problems, and we'll be applying class balancing strategies. And we'll be taking up the best performing classifier, and we'll be creating a simple web application in Flask, and we'll be serving this model at the back end of our simple web application model. And if you want, you can take this model to some cloud. And there are some free clouds available where you can run your deep learning machine learning model, and even the deep learning model with some of the limitations. Right. So we are mounting our drives because we want to access data from our drive. So that's why we need to provide it permission. And let's talk about some of the exploratory data analysis and visualization on the data. So before that, let's read our data, which is available in the CUTN folder and day2 and data.csv. So once you open that, what this data.csv contains. So it is just in the comma separated values format. Okay, so the top of the column contains the column, the top of the document contains these 12 columns. So there is ID, gender, age, whether the person is having hypertension, and then there is a listing of these values, and at last we have whether the person is having a stroke or not. So class 1 has been placed on the top, and I think then there are class 0 samples before that, and there is a highly imbalance in this data set, and it is almost 1 is to sort of 19 uh, ratio of imbalance. So we'll see that what type of imbalance is there in this data set. Right, so we have read this data set, we have imported this data set, and let's do some of the data cleaning and imputation. So why do we need data cleaning, and why should we remove some of the columns? So the first column is ID. So ID does not carry any value for the classifier. It is just a patient ID, so it is irrelevant. So if you find some of the irrelevant columns, like there is a patient's email ID or mobile number, and it is a disease classification problem or address, so that may not communicate any meaningful information to the classifier. So you can impute those values, and so let's talk about what this data set. So there are 12 columns, 5,110 rows. It is highly imbalanced data having a class sample ratio of 1 is to 19. There are 7 columns in the data set having numerical values, while 5 columns have categorical values. So categorical values are the kind of textual values, the categories. Suppose there is gender, then it may be female, male, or others. So you need to convert these categorical values into numerical values. There are 210 missing values. So if there are some missing values in the data set, so you need to overcome from those missing values, because you cannot train a classifier with the missing values. So those need to be either filled, or if you are not sure that what to fill it with, then you can simply get rid of uh, those records or samples from the data set. And fortunately we have missing values only in one column, that is BMI. So there are 210 missing values. So we'll be filling up these values, because this BMI is a numerical data. So the best strategy is to fill with the mean of, or the average of that columns value, or you can use mean or kind of mode. So mode is the most frequently occurring value. So if it is a categorical value, and you want to fill with the missing values, so you can either use the mode or you can use the mean. If it is numerical value, so it is numerical value, that's why we'll be using this mean of the column as the filler for the missing values. And so let's see the print the values from columns having categorical values. So here you get an idea that what are the categorical values and how many unique values do they have. So in gender, how many unique values are there? Ever married, what are the different column categories, just to get an idea that how these categorical values are, because you need to uh, create categorical codes in the form of 0 1 2 for these values. And let's print them. So for these 5 categorical values, there are 5 categorical values, and gender is having male, female, and other. So these are the three unique values that gender column is having. Ever married is having just yes or no. And yeah, work type is having private, self-employed, government job. And or whether they are just children or never worked. And residence type is urban and rural, and smoking status is formally smoked, never smoked, smokes, or unknown. And so the first thing is, let's drop the ID. So out of the 12 columns, we can see that only this ID column is just a kind of irrelevant, that does not convey any meaningful information, whether the person is going to have a stroke or not. So we can drop this column, and we can use the we have loaded the data set in the pandas data frame, and we can call this function from the pandas library, that is drop. And columns, we can specify here the columns, and if there are multiple columns, then we can pass as a list for multiple columns names. And uh, we are calling it on axis 1. So axis 1 represents uh, the columns, and axis 0 represents the rows. So this drop function can basically work for dropping rows and columns both, and that is decided with what axis you are working on. And there were originally 12 columns, and after performing this operation, you can see that the number of columns, after deleting one column, is 11. So one column has been deleted. And the next thing is, we can fill the missing values. So BMI column is having missing values. There are 210 missing values, and these values need to be filled with mean or average of that particular column. And so we can see that how many missing values are there uh, before filling the missing values, and after filling, whether is there any missing value in the data set or not. So print missing values before. So df dot is na, so is not available dot sum. So we can just print the missing values on each of these columns by calling this simple function is na, and dot sum. So it will provide the sum of missing values uh, corresponding to each of the columns. And print average of BMI, because we already know that BMI will be having missing values, and we can print that what is the mean of the BMI, and that mean can be used as the filler for missing values. So we want to fill the missing values in this particular column BMI. So we are using it as BF and BMI and dot fill NA. So it is, we are filling the not available values or the missing values, and the value that is used as a filler is the mean of this particular column. So you can calculate it separately, or you can just calculate in place. And yes, in places that it has to be done with this particular data frame. So you do not have to assign it, but if you do not want to change the original data frame, so you can just keep it in place equals to false. So it is just like x equals to x plus 1. So you are changing the value of x. But if you don't want to change the value of x, if you want to assign it to some other data frame, so you can assign it to some other variable by keeping it false. And we can print the missing values after this operation. So this is how it looks before filling up the missing values and after filling up the missing values. So before filling up, when you are calling this particular function, which is na dot sum, so it is finding out the sum of missing values across all the columns. In age there is no missing value, but and the rest of the other columns, but there are 201 missing values in this BMI column. And once you apply this particular operation by filling it up, these missing values with the mean of the column value, then, and again if you call the same function, then you will see that there is no missing value in our data set. So we have solved one problem, that is filling up the missing values. And length of the data set is 500, well, same original as it was. And now let's convert the categorical values into the numerical values. So there are different ways for doing that. You can have sort of one hot encoding, or you can create categorical codes. You can convert your categorical values into numerical values, and we'll be doing this by generating categorical codes corresponding to each of these categorical values. So how to do that? So first we are printing the unique values. As you can see that there are 3 unique values in this gender column. So it is male, female, and others. So we need to create codes corresponding to these values. So whenever we create codes, so they are alphabetically kind of arranged. So they are appearing randomly, male, female, and others. But whenever we'll be creating codes, so after alphabetic sorting, so whatever appears on the first place, that will be assigned value 0, and whatever comes next, that will be assigned 1, 2, and 3. So in that way we can generate the codes. And we'll be doing this in a very convenient way by creating a lambda function. So lambda functions are just anonymous functions that may be very, very handy in data processing, and we'll be seeing how to do that. But what we are doing, that whatever are our categorical columns, so there are 5 categorical columns: gender, ever married, work type, residence type, and smoking status. So for each of these columns we'll be changing their data type to category. So we'll be making them as a new data type called as category, so that we can fetch all the columns by their data type, and we can assign codes, categorical codes, to those values falling in those columns. So that is a kind of very interesting and very easy step to do. So in the first step we are converting categorical values to the numerical. We are just assigning a data type as category to all of these columns. So df gender, we are converting is at category, and ever smoke we are converting is at category. So we are just changing their data type but not the values. And cat columns, so we'll be fetching the list of all the columns by just calling this particular property dot columns. So df dot select underscore type, this is the function, and if we specify that we want to extract all those column names uh, which are having type as category. So we'll be fetching all those columns in this cat underscore columns variable. And once it is done, then we can do this transformation with this particular function that is called a lambda expression, or lambda function. So lambda functions are just anonymous functions or in place functions, just like macros, and we'll be applying on each of the columns separately, one by one. So here it is having one loop, one function, and everything, but the code that you can see is just written in one line. So what will it do? It will fetch up the first column that is of type category. So here it is gender, and it will apply this particular transformation. So for gender, it will be finding out that what are the different unique values in that particular column, and it will generate codes 0, 1, and 2. So 0 for female, and 1 for male, and 3 for other. And it will change those values to 0, 1, and 2. So this is what it is doing. And here you can see that once you print head, so the starting 5 values, so here you can see that gender, uh, earlier it was containing male, female, and others. Now it is just containing 1, 0, and 2. So these are the values, and same goes with other columns. So ever married, work type, residence type, and smoking status. So these values have been transformed into categorical values now. So these are some of the transformations that we need to do with our data set. But if you want to do some other transformations, like if you want to normalize the values to some zero mean, or you want to scale them within a particular range of 0 to 1, then you can do that. And there are different scalars and normalization functions available. You can do that. And then you can do some sort of balancing with the data set. So we'll be applying the same techniques that we discussed, smooth, to balance our imbalanced data set that we have discussed. And here smooth stands for synthetic minority oversampling technique. It is a very popular technique for balancing the imbalanced data. The current data set is highly imbalanced. So class stroke 1 is just 5% representation of the data set. The original paper on smooth suggested combining smooth with random undersampler sampling strategy. And we also saw that how it performed on our synthetic data set, where we applied a decision tree classifier, and how it improved the accuracy by simply applying without any uh, oversampling undersampling technique. It gave us an accuracy of just 76, and then with this mode is what improved to 82, and then it was further improved to 84 or 85 for our smooth and random undersampling techniques. So let's do it. And what we are going to do, that we will not kind of do it kind of 100% balancing. So we'll be following some sampling strategy. Like for smooth it will be zero point 0.4, and finally we want 1:2 ratio, or the uh, imbalance ratio of zero point 0.5. So we'll be having that strategy. And so we are importing some of the packages. So these packages you are familiar with, because we have extensively discussed them. Like what is smooth, why do we use this counter, what is underscore sampling, and what is random undersampler, what is pipeline, and how to check some of the conditions. So we'll be using this package to check the condition from numpy. Will be importing where to check a simple condition. So let's do it. First let's divide our data set into x and y's, so features and the classes. So there were total 12 features, or 12 columns in our data set. And we deleted one feature, that was id. So right now we have total 11 columns in our data set, and the last column belongs to the class label, and the starting 10 columns are our feature columns. So we are just converting our data frame into numpy array by just calling this values property. So this is just, it will just convert our data frame into numpy array, because for training we cannot use data frame. We should convert it into a numpy array. And we are doing this simple array sort of slicing and indexing. So the first represents all rows, but we are interested in these columns only. So from column index 0 to 9, so it will take starting 10 columns. The last index is excluded, and in array the indexing always starts from 0. So it will take the first 10 columns into this variable x, and it will take the last column, so that is at index 10, into this variable y. So there are features in x and class labels in y. And then we can count that how many class labels exist for this column y, that how many samples belong to class 0 and how many columns belong to class 1, and then we can print it. And further we can define our this undersampling strategy. And well, let's see how will it work. So for smooth we are having this strategy, that sampling strategy should be 0.4. So the after applying smooth, uh, the imbalance should have a ratio of zero point 0.4. So this is what we want. And finally, after applying random undersampler, we want to keep it as 0.5. So the final imbalance ratio should be 1:2. And we'll be defining these steps, first oversampling and then undersampling. And this is the pipeline where we'll be following these steps one after another. And this is the, before balancing, what is the ratio of the uh, number of samples in each of these classes. So here you can see that out of 5,110 samples, 4,861 samples are belonging to class 0, and only 249 samples are belonging to this particular class. And here you can see that there is a very huge class imbalance that is existing in our data set. And let's apply this pipeline to fit to do this transformation. So there is fit underscore resample function, and we are passing this data set features and the class labels separately, and it will do the transformation. And again we can count that what are the number of samples after this transformation. And we have applied this uh, undersampling and oversampling steps. And at last here you can see that what our data set, your number of samples in our data set is. So there are 3,888. So the number of samples in class 0 have been downsampled, and number of samples in class 1 have been upsampled, and the final ratio is 1:2. So there are 1,944 samples in our class 1, and there are 3,888 samples in our class 0. And you can print some of the samples. So that's just to see that how our data set looks like. So you can print that there are 10 values in each of these rows in X, and this is what they look like. And now they have been converted into all numeric values. And you can see that how the representation of scattering looks like. So this is just a kind of showing you that there are many samples belonging to class 0, and there are many samples belonging to class 1, and the ratio is 1:2. And now let's perform some some classification on this balanced, somewhat balanced data set that is in the ratio of 1:2. So we are calling this train underscore test underscore split, a very frequently and a very typical function that you can found in almost all the classification tasks. So here we are having 30% data for validation or for testing, and rest of the 70% data for training. And let's see that how the accuracy and other metrics uh, are there, and we'll compare multiple multiple classifiers to evaluate their accuracy and other performance parametrics. So the random state is 3 and stratify is y. So whenever we'll be doing this 30 to 70 sort of split, then it should be done in a stratified way. So the validation data set that we are having 30% samples, so that should have the proportionate representation of the minority and majority class. It should not be like that it is picking up first 30% values and putting them inside uh, you know inside our validation data, and rest of the values inside our training data. Because you saw the data set that all the values belonging to class 1, that is stroke, are placed at the top. So if it happens, then definitely again no classifier can basically classify that, because all the samples are appearing in test, and there is no sample from class 1 from in the validation. So this is what stratify means, and this is a very kind of important concept. And it is available in in validation, like whenever you are applying k-fold validation. So again there is a term called as stratified. And whenever you are splitting it, so it should be done in the form of uh, stratified way. And stratification means that if there are different classes, so this is just a kind of reservation system that exists. Like there are minority and majority, so you are kind of protecting minority, and you are having an equal proportion or equal kind of ratio when you are doing some sort of split. So after this split, let's move towards that how to do training, how to evaluate different classifiers. And we'll be evaluating there are different performance metrics available. Like there is accuracy score, classification report can give you the precision recall and F1 scores. So if you have worked on sklearn and would have evaluated mm, some classifier, then this is something that is typically used. So this is not something which is very unique. But let's create a couple of classifiers. And how you can create classifiers? So we are creating one support vector classifier, and there is svc class which is available in svm package inside sklearn. And you can call fit function. So this fit function is kind of universal, that can be applied on any type of machine learning. But whenever you are instantiating a classifier, so there are different uh, kind of hyperparameters that you can pass, and you can kind of customize them. Like with support vector machine, there is a parameter called as gamma, and you can keep it the way you want. So you will have to look into some of the documentation with svc. If you want to tweak some of the parameters for knn, then you need to look at some documentation of knn, and what are the different parameters that can be changed and customized, and can evaluate the performance based on those parameters as well. And so we are instantiating this support vector machine classifier. We are instantiating this knn classifier. We are making one instance of decision tree and a gaussian knife based classifier. And you can even create one simple neural network by creating by adding some dense layers to that network. And you can also see that how uh, a neural network architecture performs on this particular problem against these traditional machine learning algorithms, and which is the best algorithm that gives you best of the accuracy, best of the auc roc score, and best of the other performance matrix, f1 score, precision recall, and all this stuff. So we have created the instances of these classifiers, and we have stored these instances inside this classifier underscore d tree. So this is for decision tree, and we'll be seeing that how they perform on our task data set or validation data set. So after training it, let's evaluate their performance, and let's ask those classifiers to predict the labels for our features coming from x underscore val. So 30% of data is available here in x underscore val, and we want to get the predictions for these data sets, these labels, and then we will check it against y underscore val, that what are the predictions and what are the actual values, and how well they have performed. And we are calling it 4 times because there are 4 classifiers, and we are saving the predictions of our svc inside pr underscore svc, and pr underscore knn, and prediction of d3 and pr underscore d3, and the prediction of gaussian knife base inside pr underscore gnb. So this is just a very simple task for that you perform for a typical classifier. And then you can look at that the accuracy score, that how well they performed, what is the accuracy uh, that you have got from svc, what is the accuracy that you have got from knn, and for d3 and gaussian knife base as well. And the accuracy that you get is in the range of 0 to 1. That's why you need to multiply it with 100, and need to place this percent sign so that you get that this is the percentage of accuracy that you're getting. So here you can see that after balancing, we are getting an accuracy of 92.51 from SVC. And generally SVC gives you best accuracy. So either it will be decision tree or the random forest, or it will be support vector machine whenever it uh, comes to classification where the data is kind of uh, not very complicated, or it is somewhat linearly separable. Then the decision trees perform best. But otherwise, in general cases, you'll get the good accuracy. It will be top one or top two performing classifier on general problems. And you can evaluate a different you know but a different array of classifiers, multiple classifiers, can look at different validation strategies. At least should perform k-fold validation, so that you get the actual picture of their classification uh, accuracy. And so here you can see that SVC performed well, and it gave you an accuracy of 92.51. And then next is this decision tree, and then is this KNN and uh, uh, GNB. So yeah, so there are other ways, like there is decision tree, how to optimize it further. There are different tools that you can take it to the next level, like you improved or you did something with a smooth or uh, random undersampler. Then you can and suppose you got that this you are getting decision tree classifiers accuracy is 89.14, and SVC is giving you 92.51. So how to improve it further? Is there anything that you can do for decision tree? Can you optimize it with the help of random forest? And what other optimizations you can do it? So for decision tree optimization, like decision trees, the accuracy of the decision tree will be decided how well you create the split criteria. What are the different features that on which you are making your decisions, how to best optimize your Gini index, or uh, the node impurity or entropy criteria. And for decision tree, like suppose for example you can apply some sort of grid search for finding out the best decision trees. And there is a nature inspired computing subpackage available that I have appended at the last of this code book. Like if you want to optimize suppose decision trees further, so how you can apply uh, this nature inspired computing, how you can optimize decision tree generation with the help of ant colony optimization, with the help of bat algorithm, hybrid bat, take a Harris Hawk optimization, and how well they can generate the decision tree. So there is a different library which is nature inspired computing, or NIA search, that you can apply with these algorithms, especially for decision tree, to optimize it further. And suppose if you have created some neural network architecture and then you want to get the best architecture possible, then you can have neural grid search. And we discussed yesterday about AutoKeras library, where you can generate the best performing neural network candidate. So these things are getting automated, and this is what you can think of, you can optimize, you can look into to improve the accuracy for your particular piece of problem. You can compare different algorithms, different optimization criteria, different balancing strategies. And the landscape is pretty much rich. And this is what we get. And after that we'll be evaluating other performance metrics as well, like we'll be generating classification report, and classification report gives you some other parameters like precision, recall, and F score. So there are true positives, true negatives, false positives, and false negatives. So recall, precision, and F score have simple formula. They are calculated with the help of these values, and F score is just the kind of harmonic mean for these precision and recall. So after printing this classification report for these parameters for different classifiers, so this is what you get: classification report and confusion matrix that you get. So here you can see that for respective classes, how much precision, recall, and F score you are getting. And if you want to see that when there was some misclassified instances, so how they were misclassified, so that can be kind of assessed with the help of confusion matrix. It is very much used for multi-class classification problems, but you can use it for binary classification as well. So it is just a kind of a square matrix having class 0 and class 1 and class 0 and class 1 at rows and columns. So here you can see that for class 0, whatever were the number of samples, so I think there was 3,888 samples, and out of those samples 1103, but it is for validation. So out of those samples, only 30% of data was taken for validation, and out of those samples, for class 0, 1100 and 03 samples have been correctly classified for class 0, and there were 64 samples that were misclassified. And for class 1, here you can see that only 67 samples were 67 samples were misclassified, and 516 samples were correctly classified. So this is basically kind of false negatives, where it was classified as 0 but it is 1. So in healthcare, false negatives, reducing the false negatives or false positives, so you need to decide that what is more alarming, whether detecting a disease when it is not, or just not detecting a disease when it is actually there. So I think not able to detect the disease is more kind of overhead that you have, and you would like to minimize it. That if there are few instances when it is wrongly detected, so it will just take few other tests, but you can or diagnosis where you can establish whether the disease has been falsely detected. But when the disease is there and it is not detected, then it may be disastrous. So you would like to optimize and reduce these false negatives. So there are different techniques for that you can do, and here is the plot of this accuracy. And then you can export the best model. So there are because this particular model you would like to use somewhere, or if you're writing your code again, you would not like to perform the entire training process again and again, or you would like to take it forward to optimize it further, or to test it against other models. So it is better practice to save it somewhere, so that you can use it in production for testing on some real data, or you can create some application around that. You can use it at the back end of some mobile application, or you can use it at the back end of some web application. So it is a good practice to export it. And there are different libraries that you can use it for exporting, like there is pickle library, there is joblib, and there are other libraries that can help you to export it. And there are different different types of extensions by which a model can be exported, like .h5 extension and .sav are very much in use. So we'll be seeing that how to export a model in the in .sav extension, and we'll be using here joblib library. So what we are doing, where I want to save this model. So I want to save this model in my this particular drive, and I have already executed this code. That's why this model is already available here. But you need to tell the location where you want to save the model, and that can be location can be changed by this os.chdir command. We also used it yesterday, and the chdir is changed directly, so this is equivalent to cd command. And yeah, so you are changing to this particular location, so we are inside this d2 folder and cut and parent folder, and you are calling this dump function from joblib. And if you want to read it back, then you can call the load function from the same library joblib. And our best performing model was this pr underscore kind of svc, so we'll be dumping this uh, this model uh, here. And okay, it should not be pr underscore svc, it should be the name of the classifier. Right, it should be saved with the name of the classifier, so classifier underscore svc, so it should be saved here instead of this. And once it is done, then you can use this particular model for prediction. So here you are calling this function, and you can predict it, that whether it is predicting value 0 or 1. So whenever you call this prediction function, so you need to pass a two-dimensional numpy array. And the same logic can be applied, like whenever you are using this particular model at the back end of some web application or some Android app, then you can capture some of the values from the data from a simple form or user interface. You can do some sort of scaling and transformations for that data, like it should be converted into numerical values. If you did some sort of scaling on your data set during training, so you should do the scaling in that way, whether it is to be converted in the range of 0 to 1, or what type of transformations it did. And then you can pass that particular set of values in the form of numpy array, and it will give you the prediction. So this is how to export the model, how to train, classify, how to perform smooth. And since we are already at 1 p.m, so in next 10 minutes I'll be discussing with you that how to use this particular model uh, uh, as a backend model for a simple web application. And that is how to use this Flask for web application development in Python. But in the appendix, there is nature inspired computing based random forest search, where you can optimize the random forest generation, and there are different algorithms available for this optimization. And there is a package sk learn underscore nature inspired algorithms. So you will find the documentation for this package, and there are different algorithms and how to use nature inspired computing algorithms with machine learning, and for a kind of doing grid search based on that. So this is something interesting that you can kind of explore on your own. So let me just give you a very simple introduction of how to use this model uh, as the backend for some web application. Okay, so let me share my entire screen. Yeah, Chandramouli sir, do we have next 10 minutes?
Yes, sir.
Okay. Has my screen stopped sharing, or it is still there?
Still there, sir.
Okay, I think this stop sharing button is kind of not responsive.
And now it is stopped.
Okay, now it has stopped. Right. Let me share my entire screen because the code is. So now you'll be able to see my desktop.
Yes, sir.
Okay. So I'll be showing you that how to create a simple Flask application and how to kind of use this model that we just trained at the back end of your uh, web application. All right. So, okay. So the people who do not know how to use Flask and what it is. So Flask is just a very simple micro framework uh, that is written in Python and that supports Python for creating and running simple web applications. So what Flask applications are, how to set up your system for running a Flask application. You can just kind of Google a simple hello world program in Flask, like Flask hello world. So Flask is just a package in Python. It is just a library in Python that you can easily install on your system with the help of pip install. And it is better to install it in some virtual environment. So I think the people who have worked in Python would be aware of what virtual environment is. And virtual environment is just a kind of folder where you can store some of the packages that are meant for that particular task. So suppose if you want to use Flask for web application development, so it will be requiring some of the packages with some of the dependencies. But if you do not want to disturb your global environment, then you can create a virtual environment, and there are different packages for managing virtual environments, and the most simplest being VENV. So you can install it if it is not there on your system with the help of sudo apt-get install python VNV, and then you can just make a simple folder with the help of this make dir and the Flask example, and you can navigate to that particular folder, and you can create a virtual environment by calling this VENV, and it will create a VNV folder inside your that particular folder where you are working, and then you need to activate it. So for activating, if you are using Linux, then this is the command, but on Microsoft you'll have to use slightly different command. The only difference is that here you use source on Linux, and otherwise you'll have to use just VNV scripts and activate, and it will activate this particular virtual environment. And then you need to install Flask. So when you are installing Flask in some virtual environment, then it will not disturb other packages and dependencies, and you can install it with this pip install and Flask, and that is that simple. So Flask is just a package, and once you are done with that, then you can execute your Flask applications, and how to execute a Flask application. What is the basic architecture of a Flask application? So a Flask application should have, just two things. So one is this templates folder, and it should be named with just templates. And here you keep your GUI. So basically, the pages, the web pages that you would like to interact with and want to connect with your web application, you need to keep all your presentation or the design here in templates folder. So there are just two pages here, index.html and result.html. So index.html will be having simple form or GUI from where we'll be capturing the data for the 10 attributes for the model that we trained just because we want to predict whether a person is going to have a stroke or not based on the attribute values. And then there is uh, another page that is result.html. So I'll be just showing you that what the GUI looks like, and it will be rendered based on one script file that is just a Python file, and where the code is specific to Flask would be written. So here, this is the script file. You can name it with the with anything, any other name as well. You can keep it a script or you can keep it app.py. And let's see that what is the code written inside this file. So let me open it in my code editor. Okay, so this is the code written inside script.py file, and at the starting we have imported some of the packages. So the Flask, based applications, those are very much like Python code, but there are some code that is specific to the Flask. So we have imported OS package, we have imported NumPy, and we have imported this package as well, Flask, because Flask is just a package. We have imported this joblib because with this package we'll be importing our or loading our data set, and from Flask we have imported this Flask that we'll be using for running our application. Render template, with by calling this function we can display any web page, and and this request by which we can send requests or kind of redirect from one page to another. We have created an instance of this Flask class, and by default whatever is the name of this class, it will take that into account because that is a global variable. And we are making some of the mapping, that what URL will be calling from the browser and which particular function will be executed. So this is just a kind of decorator where we have the mapping between URL and the corresponding function. So if you just call this root, so the index function will be called, or if you call this /index, so then also the same function will be called. And we have defined this particular function. So whenever we'll be calling /index or just root, so root will be deciding that there will be one uh, some address, and if we just call that particular address, then this index function will be executed. What this index function is doing, it is just displaying you the index.html page, and that's it. So that is the basic purpose of the starting of the application. And then there will be some sort of some sort of transformation that will take place. So let me just first execute this application, and then let me try to explain that how it is working. So for executing this, I'll be using command prompt. So let me open my terminal or the command line here, and it has opened here. And there is one command that I need to write here, and that is export Flask app and script. So where is the script file? So that is available in the script.py file. So I'll be just exporting it, and now I can run it. Flask can run, and now it has started executing this particular code at this particular address, which is 127.0.0, and there is 5000 port, and this is how it is being rendered. So this particular page is being rendered with this Flask app, and it is a very simple kind of web page that is written in HTML, and here it is the GUI, where there are these 10 values for which I'll be entering some data, and after clicking here on get a stroke, it will be redirected uh, to the predictor, where whether the person is likely to have a stroke or not. So that is going to be predicted. Now how it is going to be predicted? So whatever values I enter here, so after filling up this form, these particular values will be stored somewhere. And for prediction, what I need to have, that I need to convert all those values in some NumPy array. So what code is being is going to execute, how it is going to execute. Let's see that. So whenever I'll be pressing this particular button, so it will be taking me to result page. So how this result page is going to execute, if request.method is post, so it will be executed only when the method is post. And to predict list, so it will be creating a list from the form, so request.form and to dictionary, so it will be automatically converting the form fields values to a dictionary, and I'll be creating a list out of that to predict list and dot value. So whatever values are there, uh, that will be converted in the form of the list, and all those values will be converted into an integer value, because by default the HTML forms, whatever values you capture are in the form of a string, so those need to be converted into integer values, and that can be done by calling this simple mapping, by converting each of the form values into integer. And then there is a list of these form values, and I'll be calling this value predictor function that I have defined, uh, that what values is it going to predict uh, based on whatever inputs have been provided with the help of this form. And this is value predictor function. What it is doing, it is converting all those values into an array, and reshaping into them one row and kind of 10 columns, so it has to be reshaped in that way. And I'll be loading this model that is available in joblib.load model svc.sav, and that is available in my current directory, which is available here, model underscore svc.sav. This is the model that we just trained, and we compared the different classifiers and found that svc is performing best. So we'll be loading this model, and we'll call this particular function predict to predict that what is the outcome of this value. And from there, we'll be taking the first prediction, and the first element, and that is going to be returned. So once this function is called, so result will be there in our this particular variable, and we'll be just checking it. If it is 1, then prediction predicts onset of the stroke, or it is if it is our ML system predicts no onset of the stroke. And render template, so we'll be calling this particular function render template, and it will display this particular file, and there will be passing one variable, and that is prediction equals to prediction. So this is the variable, and the name of the variable, global variable that we'll be using, and it's the value of this local variable that we'll be calling. And from prediction dot from this result dot html file, we can display it whatever value is being returned from here. So here from result.html, you can see that it is just a simple file, and it is displaying the value of prediction. So inside in these two curly braces, it is just a syntax of Flask to display the value of any variable that is being sent from one page to another page. So once you do this, so you can execute it, you can fill these values. Do you have hypertension, heart disease, married, self-employed, rural, or whatever, average glucose level, and BMI, and smoking, and get your stroke prediction. So once you do that, then based on the condition that is there, our ML prediction model predicts no onset of the stroke. So this is a very kind of trivial example, like how to use Flask, and time was not there to explain everything, but this is just a kind of pointer or just a kind of direction that you can explore. And that's it from my side. If you have any questions, because I think we are already overrunning of time, and the rationale to conduct this session 15 minutes, I don't know whether we could meet it or not. Yes, over to you, Professor Chandra. Yeah, am I audible?
Yes, sir, you are audible perfectly. Any queries for anyone? Okay, if there are no queries, I sincerely thank Professor Chandramani Sharma, sir.
Okay, so I'm also sharing my email ID. If you have any want to connect with me after this session, or maybe if you see the video recording, or if you get any query later on, so I've shared my email ID as well. Thank you so much. Yes, sir, please.
Yeah, I sincerely thank you for delivering the two sessions with the utmost sincerity and sharing everything what all you have discussed with the participants. And I look forward for in future endeavors also with you uh, for the Central University of Tamil Nadu. So with this, and you have got some good applications in the chat box. So they are thanking you, sir. Yeah. So with this, we'll now break for the lunch, and quickly we'll come back by 2 o'clock to start the next session.
Thank you. Bye-bye. Take care.